Um, Now, let us discuss the calculation of the electric field from the uniformly charged distribution in two dimensions. Okay. The idea is the same, that if we want to calculate the charge distribution, the charge that distribute, for example, on a plane or on a plate of object. Okay, you have charge distribute on this plate or on this 2D object. Okay, and if you want to calculate the electric field at point P, so the way to do this calculation is that you divide this object into the small pieces. Okay, this, and each piece is small enough to assume that it is a point charge. Okay, so if we can assume that this piece is a point charge, we can use the Coulomb's law to calculate the electric field. dE at point P from this charge dQ. Okay, and we must have that dE is equal to Q dQ over R squared times unit vector R. Here is the unit vector R. Okay, we have the unit vector R point from the point charge dQ to point P. So we have dE equal to K dQ over R squared times the unit vector R. Now, to calculate the total electric field, we just add up the electric field from every pieces on this object. Anyway, the way to add up the electric field, we use the integration, the calculus technique to do that job. So we have that the total electric field is equal to the integral over the entire surface of this object of dE is equal to the K dQ over R squared times the unit vector R. Okay. This is a general expression for the total electric field from this 2D object. But in a particular problem, we need to look at the treatment of this calculation separately. I mean that for a particular shape of the object, we may have to look at the way that we divide the object to be a lot of small pieces of point charge. Okay, and mainly what we have to concern a lot is about the symmetry of the object. If we use the right symmetry, the calculation will be easy or simple. But if we use the wrong symmetry, the calculation can be extremely difficult. Also, this symmetry is important when we look at the vector nature of the electric field, because the electric field of each piece is this vector, and when we add up the vector, we have to vary, or not vary, I mean, we have to look at their direction also. It means that when we add up this dE, and if we choose the correct symmetry, we can cancel some component of dE, because it point in the they point in the opposite direction, and that will reduce the calculation a lot if we use the correct symmetry. We can see this by looking at this example. This is the example 23.7. Okay. The question is that if you have the ring with the uniform charge distribution on this ring, the charge is Q, okay, and it distributes uniformly on this ring, and you want to calculate the electric field from at point P, where point P is on the axis of the ring and perpendicular to the plane of the ring at this point. Okay. The question is that what is E? Here you can see that our problem has symmetry allow the line joining the point P and the center of the ring. Okay, and you will see that this symmetry helps a lot when we do the calculation of this type. In this problem, the system is two-dimensional, but the system has two dimensions, but we can treat this using the concept of the one dimension. It means that it is because we have the thin link here. So we can say that the position of the dq can be determined when we determine the angle theta from some reference axis. Okay, so we can determine dq only by given the value of theta. So the problem is we can say it equivalently one-dimensional problem. Anyway, it happens in the chart that distribute into D. Now, the method that we use to calculate the electric field is the same. That if we divide the chart, the ring into the small pieces, a lot of small pieces like this, and then we calculate the electric field from a small pieces that we assume is a point charge at point P. Okay, so we have the dE like this. But before we go to the mathematics, before we go to the doing this integration, we can see that we can use the symmetry to reduce the calculation. How can we do that? You can see that from the symmetry of our problem, if you look at the dq here, you will have the dE of this DQ like this. But we have another DQ that lie in the opposite point from this DQ. So it's black DQ. And we will have the DE like this. And from symmetry, you can see that the vertical, not vertical, we can say that the radial component of DE, this one, the radial component of DE, in the book they use the, okay, do not give the, okay, I will give the symbol DER, and this DER will point in the opposite direction. Anyway, we can see that the distance from this DQ and this DQ to this point P are the same. Okay, I say this is R, this is R. So we have that R for the red DQ and R for the black DQ are the same. So the magnitude of this DQ, DE, the red DER and the black DER are the same. It means that these two components will cancel each other. What we have left is only the component along the axis of the ring. Okay, so we have the component. When we sum this DE, black DE and red DE, we have that this is the sum of the DE along the component. I call it the DE parallel. Okay, because this is parallel to the axis of the ring times the DE parallel of the black DQ. Okay, so this is just for one pair of the DQ on the ring. If we add up all the pair of the pieces of DQ on the ring, we can see that for every pair, the component that the radial component will cancel. We will have only the parallel component. So from this fact, it means that when we do the calculation, we need only this DE parallel, because at the end, the DE along the radial direction will cancel. So we don't have to do the calculation for this. We want to do the calculation for the parallel component of the electric field only. Okay. So how to do the parallel component of the electric field? Okay. Let's change the symbol a little. Now I will use the same symbol as in the book. So if we have the angle theta here, if we have that the radius of the ring is A, the radius is A, and the distance from the center of the ring to the point P is X, okay, we will have that the DE parallel or DEX, okay, in the book they use the DEX, so I will use the same symbol, which is the DEX, okay, and DEX. We must have that the DEX is equal to the DEX. From this figure, you can see that the DEX is this component is the component of DE along the direction of the axis of the ring. Okay, it's DE. So the DEX is equal to the DE cos theta. You can see if this angle is theta, this is the opposite angle and you must have the same value theta. Which is DE is the magnitude of this vector DE. So it's equal to K dq over R squared. Okay. We use only the magnitude here, so we don't need the unit vector R here. And cos theta. What is the cos theta? From this figure, you can see that cos theta is a ratio of R over X, right? It's a ratio of R over X. It's a ratio of X over R. Okay, it's a ratio of X over R. Okay, that is the cos theta. It's a X over R. Okay, so we have the expression for the DEX. Now, we want to calculate. You can see that. Now, we know exactly what is the direction of the total E. Because we know that the component, the radial component will cancel. So, the vector E must have the direction along the axis of the ring. So we don't have to worry about the direction of E anymore. What we need to do is to calculate the magnitude of E. So the magnitude of E must equal to the sum up of this DEX because the DER cancel. All DER cancel. So we have that E is equal to the sum up or integral of DEX, which is equal to the integral of K dq over R squared X over R. Okay. Now you can see that from this configuration, the distance from each piece of DQ to the point P is a constant. You can look at any piece on the ring and the distance R is a constant. Also the distance X is a constant. So it means that X and R is a constant in this integration. K is a constant, is an electric constant, R is a constant as I have explained. So all of these terms can be taken out of the integration. So we have that is equal to the K X over R cubed. Okay, of the integration of dq. Now, what is the integration of dq? As I explained many times that the integration is just a summation of dq. So when we do the integration of dq, it means that we sum all of the value of dq for every pieces on this ring, and it must equal to the value of q. Right? So we have that this equal to the kx over r cubed of q times q. That is the solution. Okay. Anyway, if we want to write down r explicitly in terms of a and x, you can see that we can write this as kx cubed over